students are present at this point? 27 students. Okay. Okay, anybody else? Any volunteer who wants to describe what a beam is?
Assalamualaikum, sir.
Walaikum salam. Okay. What's your roll number?
36.
36. Okay, 36. Please go ahead.
ये जो डिफरेंट लोड्स वर्टिकली इसके ऊपर सेट कर रहे होते हैं, उनको डिवाइड करके वो बुनियादों के ऊपर वजन डाल देते हैं डिवाइड करके.
Okay, so you mean to say that beam distributes load and it
Yes.
finally transfers the load to foundations.
Yes, sir.
Okay, so if we want to define beam, a proper definition would be that beam is a structural member that is normally subjected to transverse loading, and the internal forces generated in the beams in the beam are shear force and bending moment. Further, the orientation of beam is normally horizontal, but it is not necessary. It can have any orientation. Now, when I define the beam, I say that it is a structural member. So there are a few important terms in this definition. So I said beam is a structural member. Now, what do we mean by a structural member? Basically, there are two types of members: structural members and architectural members. Structural members and architectural members. What do we mean by a structural member? A structural member is basically a load carrying member. Load carrying or load bearing member. And architectural member is just there for the sake of aesthetics. Structural member is a load bearing member, and architectural member is just provided for the sake of aesthetics. So beam is a structural member, means beam is a load carrying member. When we provide a beam, it's a purpose to the other part of the structure. Normally, not in all the cases, but normally the beams are provided inside or underneath the slabs. So they take loads from slabs and they transfer loads to columns, and from columns load transfers to foundations. So beam is a structural member, one thing is for sure. It is not an architectural member. And is there any example of an architectural member in a structure? So one example of an architectural member is false ceiling. Just for the sake of aesthetics, for the sake of beauty or looks, it does not take care of any load. So such members are termed as architectural members. So coming back to beams, beam is a structural member, and further it takes care of transverse loading. Now, what do we mean by transverse loading? If we have this member, this horizontal member, let's say this is a beam, then the load that is acting perpendicular to the longitudinal axis of the member. What is longitudinal axis? Longitudinal axis runs along the length of the member and it passes through centroid of the cross section. I will show it with the diagram later on. So if we have a beam, if we have a member, a structural member, which is subjected to transverse loading, means loading perpendicular to the longitudinal axis of the member, that structure is termed as a beam. And the internal forces developed in a beam are shear force and bending moment. In a short while, we will discuss that. What do we mean by shear force and bending? And next thing comes about the orientation of beam. In most of the cases, beams are horizontal. That is why sometimes students assume that beams are always horizontal, but that is not the case. As a structural engineer, the behavior of member is more important for us. We say that beam is a structural member that is subjected to transverse loading, and the internal forces developed are shear force and bending moment. So if you have this member, but it is subjected to, let's say, compression, I try to compress this member, then this member will no longer behave as a beam. Rather, this member will start behaving as a column, because columns are the members that are primarily subjected to axial compression. By compression, I mean a load that tries to compress a member, and by tension, we mean a load that tries to elongate a member. The member and tries to elongate it. So in case of beam, we have transverse loading. As an architect, maybe we can say that beams are always horizontal, because architects are basically concerned about the physical structures. We are concerned with the structural behavior. If the behavior,
सर आपकी आवाज़ काफ़ी लैग कर रही है.
it is categorized as was lag correct. Okay. Now apparently the signals are big, so I hope it gets better automatically soon. Or what I can do, I can switch to the other network. Just give me a moment. All right, so I have changed my network. I hope this will work better. Okay, so is everybody clear about beams? Any question about beams? If you have any question, you can raise your hand. Okay, if you do not have any question about beams, just type 1 in the chat box. I want to see your response. Type 1 in chat box. Like this. Type 1 and press enter. Okay, rule number 28, please go ahead.
स्टूडेंट सर ट्रांसवर्स लोड के हवाले से जो आप कह रहे हैं कि तो ट्रांसवर्स लोड बस उसमें लगना है.
Transverse load. Okay, let me explain it again. What do we mean by transverse load? Okay, this member, a horizontal member, right? Where is the longitudinal axis of this member? It runs along the length of the member. Okay, and what do we mean by transverse load? By transverse load, I mean any load that acts perpendicular to the longitudinal axis of the member, like vertical. If the beam is horizontal, then the transverse load in this case will be vertical, and this load is termed as transverse load, and as a result of this load, shear force and bending moment, these two internal forces are developed in the member. So if we have a same horizontal member, but I apply axial compression on that, means I try to compress the member from both the ends, this type of load is termed as axial compression, and the behavior under this type of load will not be a beam-like behavior. It will be more like a column. So when we will design this member, we will design it as a column, although it is horizontal. Okay, although in most of the cases beams are horizontal and columns are vertical, but that is not something like absolute truth. We can have inclined or vertical beams. If we have a vertical member and the load is acting transverse to the longitudinal axis, then the behavior of this vertical member will be like a beam. It will bend like this, like out of plane, and then it will its behavior will be like a beam, and it will be analyzed and designed like a beam. So the nature of loading is important while defining the behavior of any member. So if we have,
So you means to say that beams shouldn't compress.
there may be slight compression in the beam, some compression, but the main force, dominant forces are shear forces and bending moments. There may be slight compression present. There is a limit for that. We will not be talking about that at this stage as a beginner. As a beginner, we will always be considering pure beam behavior and pure column behavior. There is another type of member that lies in between beam and column. That is termed as a beam column. But we will not be talking about a beam column at this stage. We will just talk about beams and columns separately. And in our case, in case of beams will have transverse forces like this. This is the longitudinal axis of the beam, and this is a transverse force. Let's say span of beam is 5 meters, and this force is, let's say, 10 kilonewton or whatever. Okay, so this is transverse load acting on the beam. So this structural member is a beam. Is it clear now?
Yes, sir. Thank you.
Okay, you're welcome. Rule number 18, please go ahead.
Assalamu alaikum, sir.
Walaikum assalam.
Sir, can a cube act as a beam?
Can a cube?
Yes, sir. Because it has same length and height.
Yes, I don't think so. Unless like you, because its cross-sectional dimensions are same as that of span. But there is a thing that is termed as deep beam. Probably if you have a cube type member, but you provide two supports like this and you apply a load here, it might have some bending movement and shear force in it, but that would be different than the normal beams like this. So it will be a different case. It may act like a deep beam, but normally we do not encounter this type of situation. The spans of beams are much longer than the cross-sectional dimensions. So at this point, I would say no. Okay. Okay, roll number 22.
सर अगर कोई बीम है और उसको थ्रू आउट द लेंथ सपोर्ट किया गया है, जिस तरह घरों में होता है कि बीम होता है और नीचे से ईंटों से उसको सपोर्ट होती है, तो वो बीम ही होगा या फिर वो स्ट्रक्चरल मेंबर बीम नहीं रहेगा अगर वो थ्रू आउट द लेंथ सपोर्ट?
अगर if it is supported throughout the length, actually it depends that when have you provided that wall. Supposedly you have a beam here and these two supports were present at the beginning, and once you constructed the beam, the structure was complete. Later on, if you construct a wall here, these are bricks, you build a wall underneath at later stages, and the beam has already deflected or already taken care of the applied load, then in that case the beam would still be a beam. If this wall is constructed at later stage, initially the beam was built and the beam was subjected to some loading and the beam took care of that load, and later on you just built a partition wall underneath, then the beam will still be a beam. Okay, but if the beam is supported like right at the beginning, the wall is there, and for some reason, normally we don't do that you have casted a member on top of this wall, then that member will not behave like a beam. Okay. All right. So after this basic definition of beam, let's move to the definition of supports. There are different types of supports. This is again something very basic, and we need to clearly understand different types of supports. So do you guys know any types of supports?
Yes, sir.
Okay, 22, please go ahead.
Sir, roller support, hinge support.
Roller support, hinge support, Okay. Any other
Yeah.
type? Roller
So
and
fixed
hinge,
support,
both are correct. Fixed support, that's
fixed
very right.
support.
So these are right. These are three types of supports: roller, hinge, and fixed. And can any one of you explain the difference? What is the difference between these types of supports? Raise your hand if you want to explain this. Every time you want to speak, just raise your hand. Okay, Asim, please go ahead.
सर हिंज सपोर्ट में हम इसमें ये बेंडिंग भी बियर कर सकता है, यानी कि एक पॉइंट पर ही, क्योंकि वहाँ पर फिक्स हुआ होता है, तो और रोलर में
Point.
ये एक्सपेंड और एक्सपेंशन और कॉन्ट्रैक्शन की वजह से ये वो भी कर सकता है, यानी कि रोल भी कर सकता है उस पर, इसीलिए रोलर सपोर्ट दिया जाता है टेम्परेचर चेंजेस की वजह से। और फिक्स सपोर्ट में कुछ भी नहीं है, दोनों में बेंडिंग भी नहीं हो सकती, ना वो कंप्रेशन कॉन्ट्रैक्शन कर सकता है।
Okay. Okay. All right, that makes somewhat sense. Let's see these types of supports one by one. So first type of support, the simplest one, is roller support. Roller support. Second type of support is hinge support. And third type of support is fixed support. Well, now, what is roller support? Roller support has the capacity to generate one reaction only. Roller support can generate only one reaction, and that reaction is normal to the supporting surface. This is the supporting surface, and the reaction generated in case of rolling, in case of a roller support, is normal to the supporting surface. Okay, whereas hinge support can generate two reactions. So roller support, one reaction. Hinge support can generate two reactions, and these reactions are perpendicular to the supporting surface and parallel to the supporting surface. And fixed support can generate three reactions, and these reactions are parallel to supporting surface, perpendicular to supporting surface, and resisting movement. Roller support, one reaction. Hinge support, two reactions. And fixed support, three reactions. Now, one important thing to note here is sometimes students define roller support as the one that can generate vertical reaction only. But actually, this is not a 100% correct definition, because sometimes we provide roller support in a different orientation. For example, like this. Now, this is a structure which is a combination of a column and a beam. And let's say if I provide a roller support here like this. Now, what will be the direction of reaction generated at this roller support? Will it be
Horizontal.
vertical? It will be horizontal. That's very right. So defining roller support as the one that can generate vertical reaction only is not correct. It depends upon the orientation of roller support, right? So roller support is a support that can provide reaction perpendicular to the supporting surface. Hinge support is the one that can provide reaction perpendicular to the supporting surface and parallel to the supporting surface. And fixed support is the one that can generate reaction parallel to the supporting surface, perpendicular to the supporting surface, and a resisting movement. So there are three reactions generated in case of a fixed support. And all these supports may be provided in a structure in different orientations. Sometimes in this orientation, sometimes a roller is provided in vertical orientation, and even in sometimes we have inclined members and we have supports at the end of inclined members. For example, we might have a structure like this. And in that case, we will have 3 reactions here, and we will have 2 reactions here. Now these reactions are not vertical and horizontal. These reactions are again parallel to the supporting surface and perpendicular to the supporting surface. So whenever you define a roller support, you say it's a support that can generate reaction perpendicular to the supporting surface. Hinge support can generate reaction parallel and perpendicular to supporting surface. And fixed support can generate 3 reactions, parallel, perpendicular, and resisting moment. Everybody is clear about these types of supports?
Yes, sir.
Okay. We have some more students join the meeting, so let me change their status to attendee. All right. So roll number 48. 48, are you there? Are you listening? Roll number 48.
Yes, sir, I am listening.
Listening. Okay, 48. Can you now describe these 3 supports?
Rigid support, it generates perpendicular support.
Oh, is it a rigid support? What's written here? It's written on the screen.
Roller support.
Roller support. Okay, so roller support.
Yes, sir. Hinge, then hinge generate reaction both perpendicular and parallel to support.
Supporting surface. Okay. Then what about fixed?
Fixed, it generate 3 supports, 3 reactions that are perpendicular, parallel, and bending.
Perpendicular, parallel, and bending, and resisting movement. Okay, now thank you. Now one question is that how do we provide these supports in real structures? So a simple example would be for let's say this is a beam. So if we want to provide a hinge support, hinge support is provided like this, and roller support is provided like this. You can see that in this case, this is a column and this is beam. The column is not providing any restraint or any restriction against the horizontal movement. So this is a supporting surface, and the structure or the support can provide reaction only against the supporting surface. In this case, we can have a reaction in this direction as well as in this direction, vertical reaction as well as horizontal reaction. So if I want to draw a free body diagram of this structure, the free body diagram would be somewhat like this. This support is a roller support, and this support is a hinge support. Okay, so this is how we provide these types of supports in case of real structures. So after these different types of supports, now let's move to different types of beams, because depending upon these different types of supports, the beams are divided into different categories. So next is types of beams. Okay, is there any question? Okay, 28, please go ahead.
Yes, sir. Please give the example of fixed support. How to provide that?
Okay, yes, sure. I missed that. For fixed support, let's say I want to provide fixed support for a beam. How would I do that? This is a beam. It's a column. This is how fixed support is provided. The beam is embedded inside a column, and this column has to be really rigid column, like reinforced concrete column. That will have the ability to provide all three types of reactions. So this is this arrow is not. This is a separate drawing figure. So this is a roller support and this is a hinge support. Did you get it?
Yes, sir. Thank you.
Okay, you're welcome. So now let's come back to types of beams. So have you guys studied any types of beams? Anyone? Can anyone give us some idea about types? Okay. There's 36. Okay, simply supported.
Yes, so simply supported beam.
Okay.
Overhanging.
Overhanging.
Cantilever. Cantilever.
Okay. Cantilever. Okay, that's correct.
Continuous beam.
Continuous beam. That's right.
Yes.
Okay.
These are the.
That's it. All right. So simply supported beam. What is a simply supported beam?
तो इसके दोनों कॉर्नर्स पे जो हम सपोर्ट देते हैं उसे सिंपली सपोर्टेड बीम कहेंगे.
जिसके दोनों कॉर्नर्स पे, and these can be like any supports.
The perpendicular
Fixed support that.
Oh, okay. So rule number 28 thinks that we provide fixed support in case of a simply supported beam. Anybody else wants to define a simply supported beam? 35. 35. Can you hear me?
Yes, sir.
Okay. Any idea about a simply supported beam?
No, sir.
No idea? Okay. 43. 43.
Yes, sir.
Can you give us some idea about a simply supported
Sir,
beam?
maybe sir, we give support for roller supports maybe.
Roller support. So there are two roller supports.
Yes, sir.
Okay. Akbal, you raised your hand.
Sir, one is roller support and the other is hinge support.
Okay. Yeah, actually that is correct. So in case of a simply supported beam, we have one hinge support and one roller support. So this is the diagram of a simply supported beam. So this is a simply supported beam. In this case, we have a hinge support and a roller support. So this is one of the most common types of beams, simply supported beam. Another type of beam is a cantilever beam. A cantilever beam has one fixed support and the other end is free. So this is a cantilever beam. And then we have an overhanging beam. What do we mean by an overhanging beam? One end of an overhanging beam projects beyond the beyond the support. So this type of beam is termed as overhanging beam, and this projected end may be on both sides as well, right? Sometimes we call this type of beam as single overhanging beam, and if we have projections on both the sides, we call that as double overhanging beam. But technically or analysis wise, the procedure is exactly the same to incorporate one overhang or two overhangs. If it's on this side, we will consider it the resulting movement on this side. If it's on the other side, we will consider the movement on the other side as well. When we'll go into the analysis, we will see that what difference does it make. So simply supported beam, cantilever beam, and overhanging beam. Next type is fixed ended beam. Fixed ended. So next type of beam is fixed ended. In case of fixed ended beam, we have fixed support at both the ends. So in case of a fixed ended beam, we have fixed support at both the ends. And then there is another type that is termed as continuous beam. If a beam has more than one span, it is termed as a continuous beam. For example, this one. And now what do we mean by span? The part of the beam or length of the beam present in between any two supports is termed as span. So this beam has one span only. This beam, although it does not have any support at the other end, but this length is still termed as span of the beam. From this support to this support is the span of the beam. This is span of the beam. In this case, we have two spans. Span 1 and span 2. So a beam that has more than one spans is termed as a continuous beam. And then the last type is propped cantilever beam. Okay, this is continuous. Continuous beam. This is propped cantilever beam. So these are 6 common types of beams. If you study the literature, you might find some other types as well, but these are the common ones. That is why we are covering here. Simply supported beam, one roller support, one hinge support. Cantilever beam, just one fixed support, other end is free. Overhanging beam, hinge support, roller support. Basically, it's about the projected part. Otherwise, we might have different, like even if we have here, even if I swap the hinge and roller, it doesn't make any difference. It will still remain as a an overhanging beam. Fixed ended beam, both ends are fixed. Continuous beam, more than one spans. Propped cantilever beam, one end is fixed, other end has hinge, either a roller or a hinge. Even if I have a hinge support here, that will still remain as a propped cantilever beam. So these are 6 common types of beams. Now, after these types of beams, there is another concept that's about determinacy. Determinate beams and indeterminate beams. Have you guys heard about this concept? Will anybody explain about the determinacy and indeterminacy? Anyone? Okay, roll number 22. 22, are you there?
Yes, sir.
Okay, so any idea about determinacy and indeterminacy, or a determinate beam and indeterminate beam?
No, sir.
No idea at all. Have you ever heard this term?
No, sir. First time I heard this term.
Oh, really?
Yes,
Anybody
sir.
has anybody in the class ever heard this term, determinate beam or indeterminate beam or degree of indeterminacy? CR?
Assalamualaikum, sir.
जी
Walaikum
सर
salam. 36, you are CR?
Sir, no, sir.
Okay. Who is CR?
यस सर
20.
CR, what's your roll number?
सर 27
27. You are Asim.
यस सर
Okay. Asim, have you ever heard about determinate and indeterminate beams?
नो सर हियर फर्स्ट टाइम
First time. Okay. 36, you wanted to say something.
सर यही डिटर्मिनेंट इसी को कहते हैं कि अगर आपको सारे लोड्स और रिएक्शंस की वैल्यूज फाइंड हो.
Fine. Okay. Determinate beam. Okay. I see a hand raised. Please go ahead.
Sir, I think so. If we talk about determinate structures, then we can say that for this structure, if we want to calculate the reactions, all the reactions, then we can apply equilibrium conditions, and these can satisfy. But if we talk about indeterminate structures, then equilibrium conditions or equations cannot help us to find out all type of reactions for that specific structure.
Yeah, that's right. That's right. So you guys studied this in basic mechanics, right?
No, sir.
No? Where did you study this then? I'm just curious.
So Google.
Is it Google? So you just Google it right now?
Yes, sir.
Okay, you don't have to do that, but anyways, that's fine. Okay, that's good. Determinate structure and indeterminate structure. This is a very important concept, determinacy and indeterminacy. Any structure, okay, any structure that can be completely analyzed just by using three conditions of equilibrium, that is termed as a determinate structure. And why I'm saying that three conditions of equilibrium? Because right now we are talking about two-dimensional structures. In two-dimensional structures, the structure, all the applied loadings and reactions are in a 2D plane. So if we have a two-dimensional structure, all the forces and reactions are in a 2D plane. So if for a given beam, we can analyze the beam, or we can find out the reactions of the beams just by using three conditions of equilibrium, that type of beam is termed as a determinate beam. Or in other words, we can say that if we have three reactions, then we can analyze that beam using conditions of equilibrium, and that beam is a determinate beam. Now let's see the examples that we have just seen, whether they are determinate or indeterminate. We have a simply supported beam. How many reactions can be generated in a simply supported beam? 1, 2, and 3. So there are possibly 3 reactions can be generated for a simply supported beam. And how many conditions of equilibrium are there? If I write it down here, or equations of equilibrium. Equations of equilibrium. You guys have studied that. Sigma fx equal to 0. This is for a 2D system. Sigma fy equal to 0 and sigma mz equal to 0. These are the three conditions of equilibrium. If this is my nomenclature, or convention. X-axis, Y-axis, and Z-axis. X and Y, X is the horizontal axis in plane, Y is the vertical axis in the plane, and Z is out of plane axis. It is this axis basically. Okay, so if these are the three axes and a system is present in XY plane, then these are the three relevant equations of equilibrium. Sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0. So if we have a beam that has three reactions maximum, that beam can be analyzed using these three conditions of equilibrium. So that beam is termed as a determinate beam. Simply supported beam is a determinate beam. How many reactions can be generated in a cantilever beam? 1, 2, and 3. So this beam is also a determinate beam. How many reactions can be generated in an overhanging beam? 1, 2, 3. So three reactions are there, three conditions of or three equations of equilibrium. It means that again this overhanging beam can be analyzed using these three equations of equilibrium. So these three beams are determinate beams. Now what about fixed ended beam? How many reactions? 1, 2, 3, 4, 5, and 6. So we have 6 reactions in case of a fixed ended beam. Can we solve or can we determine 6 unknowns using 3 equations? No, we cannot do that. So if we cannot do that, it means this beam is an fixed ended beam is an indeterminate beam. Now let's move to continuous beam. How many reactions? 1, 2, 3, 4. This continuous beam has 4 reactions. Can we analyze or can we determine 4 unknowns using 3 equations? No, we cannot do that. It means this is an indeterminate beam. What about a propped cantilever beam? We have 1 reaction here, 2, 3, and 4 reactions. So in case of a propped cantilever beam, we have 4 reactions, but we have only 3 equations of equilibrium. It means that even a propped cantilever beam cannot be analyzed using these 3 conditions of equilibrium. So this propped cantilever beam is also an example of an indeterminate beam. So these 3 beams are determinate beams, and these 3 are indeterminate beams. So first 3, simply supported beam, cantilever beam, and overhanging beam are the example of determinate beams. And next 3 are the examples of indeterminate beam. Okay, is there any question? Okay, 22, please go ahead.
सर जो कंटिन्यूस बीम है इसके स्पैन 1 और 2 को अगर अलग अलग एनालाइज करना चाहें तो फिर हम इन इक्वेशंस के जरिए कर सकते हैं?
Actually that will make an entirely different system. We cannot simply break a continuous beam into 2 simply supported beams. We cannot do that. For these indeterminate beams, there are other methods available that you will be covering maybe next semester or next to next semester when you will be talking about structural analysis. Okay, in this semester, all our discussion will be about determinate beams. But as it is important for you to understand that what is a determinate beam and what is an indeterminate beam. That's why we are discussing that. Otherwise, in this semester, we will not learn the methods to analyze indeterminate beams. All our discussion will be focused on determinate beams. Okay?
Yes, sir.
Okay, Akmal, please go ahead.
Sir, while analyzing a beam, do we consider the friction between the support and the beam?
At this point, no. We do not consider that. Like for example, if we have a roller support, then we are saying that roller support can generate reaction normal to the supporting surface only. But due to the surface friction, it can generate some magnitude of horizontal reaction as well because of the friction, but we do not consider that. So at this stage, we will not be considering that. Even at later stages, we don't do that. Okay.
Okay, sir.
All right. So these are determinate and indeterminate beams. Now there is another concept that is known as degree of indeterminacy, but it's 9:03. At this point, we can have a break for 10 minutes. And after that, we will continue our discussion. But one thing, our session is still on and the recording is still going on. So be careful if you are talking to each other or anything, it will be recorded and it will go online. Okay, so be very careful. So we will just stop here and we will take a break for 10 minutes. It's 9:04, so we'll start at 9:14 again. Okay, so I'm still here in the meeting. I'm just muting my mic. All right, so see you at 9:14. Okay guys, so this is 9:14 a.m. So let's start again. Can you guys hear me? Everyone?
Yes, sir.
Yes.
Okay. Asim, you can hear me?
जी sir.
Okay. And can you guys see the video or like the kind of board in this case, the camera view?
Yes, sir. Clearly visible.
Okay, that is great. All right, and yes, one more thing that I see the current number of attendees are 28. So the attendance is pretty low. I will be keeping track of attendance. So I took one attendance close to the beginning of the class, and I have taken attendance one more time just a few minutes ago. So make sure that you attend the classes and you attend the entire class. You appear at 8 a.m. sharp and then you stay till the end of the class, okay? Because your attendance is going to contribute to your grade finally. All right, so we talked about determinate and indeterminate beams. Now after this, next concept is about degree of indeterminacy. Degree of indeterminacy. Degree of indeterminacy. Now, what is degree of indeterminacy? The degree of indeterminacy is the difference between number of reactions and the number of available equations. For example, if I abbreviate degree of indeterminacy as DOI, so degree of indeterminacy for a simply supported beam would be what? How many reactions are there? 3 reactions. How many equations are available? 3 equations. So 3 minus 3 equal to 0. So degree of indeterminacy of a simply supported beam is 0, and that is why it is a determinate beam. Let's move to a cantilever beam. Degree of indeterminacy of a cantilever beam. How many reactions are there? 3 reactions. How many equations? 3 equations. 3 minus 3 is equal to 0. So degree of indeterminacy of a cantilever beam is 0. That's why it is a determinate beam. Next is this overhanging beam. How many reactions? 1, 2, 3. So degree of indeterminacy is 3 minus 3 equal to 0. There are 3 unknowns and 3 equations. So degree of indeterminacy is 0. That is why these 3 beams are determinate beams. What about a fixed ended beam? How many unknowns are there? 1, 2, 3, 4, 5, 6. How many equations are there? 3. So degree of indeterminacy is 3. What degree of indeterminacy tells us basically is that how many more relationships between the knowns and unknown parameters are required in order to analyze the system. So this number 3, degree of indeterminacy, is telling us that other than these 3 equations of equilibrium, we need 3 more relationships between known and unknown parameters, and then we will be able to analyze the system. Okay. Now, what about this continuous beam? If I write it down here, let's say degree of indeterminacy. How many reactions? 1, 2, 3, 4. 4 minus 3 equal to 1. So degree of indeterminacy is 1. What about this propped cantilever beam? 1, 2, 3, 4 reactions and 3 equations. So 1. Degree of indeterminacy is 1. Okay, is there any question? I see something on my Teams. Okay, no, there's no question. Fine. So this is how we calculate degree of indeterminacy. First of all, we see how many unknowns or how many reactions are there. Then we see how many equations of equilibrium are there. For 2D system, these will always be 3. And we take the difference, and that difference gives us degree of indeterminacy. And the importance or significance of degree of indeterminacy is that it tells us about the number of additional relationships that will be required in order to analyze the system. So I can write down the formula for degree of indeterminacy here as well. Degree of indeterminacy is equal to number of unknowns, or in other words, reactions, minus number of equilibrium equations. Okay, everybody is clear about this? Anybody having any question about determinacy and indeterminacy? Or how do we calculate it? If you have any question, raise your hand. Okay, no question. All right, then let's move ahead. Now, with this concept of determinacy and indeterminacy, there is another associated concept that is termed as stability. Okay, one clarity before going to stability about the determinacy and indeterminacy. Like, indeterminacy is not a bad thing. We don't say that, oh, these structures are indeterminate, so these are like bad structures, or these are some unwanted type of structures. Depending upon our requirement, we construct beams and we provide supports, whether ultimately they are determinate or indeterminate, because we have methods available to analyze indeterminate beams as well. But what bad is, there is instability. Stability of a beam is important. So when we analyze the beam, we check the stability as well, that the beam should be stable. If it is determinate, it means it is easier to analyze. If it's indeterminate, it means it is hard to analyze, but that's fine. But if a beam is unstable, it means that is an unsafe beam. We don't want our structure to be unstable. We want to make stable structures. So instability is a bad thing. Otherwise, indeterminacy is not a bad thing. Okay. Now, for stability, there are two conditions that should be satisfied. Number one, there should be at least 3 reactions. At least 3 reactions. And second condition is all of them should not be parallel to each other. So we need, these are the two conditions that should be satisfied in order for a structure to be stable. There should be at least 3 reactions, and all those reactions should not be parallel to each other. Now let me give you an example. For example, a simply supported beam, how many reactions are there? 1, 2, and 3. So this beam is a stable beam, all right? And you see that all of them are not parallel to each other. 1 and 2, like these 2 reactions are parallel to each other, but the third one is not parallel to the other 2. So that's why this is a stable structure. Now let me give you an example of a beam that has 3 reactions, but it is still unstable. For example, if I make a continuous beam like this. Oh, not visible. Okay, so this is a continuous beam, and this continuous beam has 3 roller supports. Now, how many reactions will be generated? There will be 3 reactions. So the first condition of stability is satisfied. There are 3 conditions available, 3 reactions available. But is the second condition satisfied? All of them should not be parallel to each other. All of them are parallel to each other. So this structure, if I apply a horizontal load in this structure, let's say I apply an inclined load, and that inclined load will have a vertical component and a horizontal component. So under this horizontal component, the beam will have the tendency to move in the horizontal direction, and none of the support can restrict that horizontal movement. And ultimately, the beam will slide off the supports. So such beam is an unstable beam. Unstable beam. And unstable structures are undesirable. We do not want our structures to be unstable. So we will avoid this type of structure in practice. Okay, is that clear? Anybody having any question about the stability? Stability or indeterminacy? Okay, roll number 22, please go ahead.
सर ये अपने वेट की वजह से बीम रेजिस्टेंस क्रिएट नहीं करेगा हॉरिजॉन्टल जो है फोर्स को, वो अपनी वेट की जो उसका वेट होगा.
Yeah, I got your point. There will be minor resistance against the horizontal movement, but we don't want the structure just to demonstrate resistance against the horizontal loading on the basis of self weight only. And one clarity here is that when I say roller support, some of the students sometimes think that there is an actual physical roller present in the structure. So just to be clear, that is not the case. When I say roller support, it does not mean that we will provide a physical roller like a cylinder type shape or a ball type shape under the support. That type of support is provided in a very few cases. For example, in case of bridges, especially steel bridges, when we expect a lot of expansion in the structure and we want the structure to move in the horizontal direction very smoothly and easily, then we provide physical rollers under the support so that the structure can easily move over that support. Otherwise, roller support does not mean that there will be a physical roller. And as he pointed out, and as I said earlier as well, that even roller support has the ability to provide small magnitude of horizontal reaction. But at this stage, at this point, we will be ignoring that. We will not say that, oh, there is slight horizontal force, so the self weight will make it stable. No, if it's a roller support, we will assume the horizontal reaction is zero. Again, just for clarity, practically it will be able to provide some resistance, but we do not want to depend upon that small magnitude of resistance. Okay, is that clear?
Yes, sir.
All right. So this was about stability and instability. Next, there are beam shapes, and by this I mean beam cross-sectional shapes. Beam cross-sectional shapes. You guys have already studied civil engineering drawing, so you know what do I mean by a cross-section. Like if this is a member, then if I cut a section here and I look at the shape of the beam, that is termed as its cross-sectional shape. So right now we are going to talk about the cross-sectional shapes that we provide in beam structures. When we are drawing shear force diagram or bending moment diagram, normally we are not concerned about the cross-sectional shapes. But in case of stress calculation or deflection calculation, the cross-sectional shape is important. So the most common type of cross-sectional shape is a rectangular shape. A rectangular shape. Another type is T-shape. Sometimes we make the cross-section of a beam of a T-shape. And another type is I-section. Although this I-section is a layman language, technically we call it a W-section, wide flange section. but you will learn that later on. Why do we call it a W section? So at this point, you may call it an I section. And this part of T section and this part of I section is termed as web. Okay, and this part of T section, the horizontal part, is termed as a flange. Similarly, this part of a W section or I section is termed as a flange. So these horizontal elements are flanges and these vertical elements are webs. And sometimes we also provide a box section. So this is hollow box section. Hollow section. And we also provide C section or channel section. This shape is termed as C section or channel section. Sometimes we provide L sections as well, not very frequently, but in some cases you will see that. Okay, so these are different cross-sectional shapes of beams that we might be dealing with in future. Okay. Okay, one thing, although I will be providing all this recording to you guys, but I strongly recommend all of you to note down the lecture, to make notes, because experience shows that whenever we take notes, we develop a better understanding. So I would suggest you, as I'm writing here, you guys also write down, take notes and make your proper lectures. Okay, although all these recordings will be available to you for your future reference. Okay, so these were the different cross-sectional shapes that we will be dealing with in future. Okay, now with these cross-sectional shapes, now let's move to different types of loadings. Is there any question? Okay, I don't see any hand raised. Okay, so now let's see different types of loadings. Types of loads. Okay, and these are the types of loads with respect to distribution. Can anybody tell me what are different types of loads?
Yes, sir.
Okay, please go ahead.
So point load.
Point load. Sorry, I could not hear you. Point load and then?
And UDL, uniform distributed load.
Okay, that's right. What else?
So UDL, sir.
UDL is the second type.
So उसके
Any
बाद
other type?
ये सर थर्ड टाइप है उसका वो varily distributed load. Varily load is the yes.
Okay, that's right. So there are three types of loads that we will be dealing with. So we'll be dealing with a point load. Okay. Now, what do we mean by a point load? If I have a beam like this, let's say it's a simply supported beam, and I apply a single load here. Supposedly its magnitude is P and span is L. So this type of load is termed as point load. The load which is concentrated at a single point is termed as point load. And the example of such load is that, for example, if I have a beam and let's say a brick wall or a brick column is constructed over this beam, So this column will apply a point load on this beam, right? And one clarification here is that when we draw a free body diagram, we show point load with just a single arrow, and it appears that it is acting on like just one point, very like just one point, but actually this is not so. Point load acts on a certain area, but the thing is that this area is very small as compared to the overall geometry of the structure. That is why we treat that load as a point load. So this first type is a point load. After the point load, the next example or the next type is a uniformly distributed load. So if I have a simply supported beam and the load is distributed all along the length or all over the area, we call that load as a uniformly distributed load. And the intensity of uniformly distributed load is omega. There are two ways to show a uniformly distributed load, especially when we are doing manual calculations. We do not bother to make these rectangles, we just show it like this. That's a quick way to show a uniformly distributed load. Okay. So this type of load is termed as uniformly distributed load and abbreviated as UDL. Uniformly distributed load or UDL. And the example would be that if we have a beam and we have a wall constructed over that beam. So that wall will apply a uniformly distributed load over the beam. All right. So if we have a beam and we have constructed a wall over the beam, that wall will apply a distributed load on the length of the beam. And how do we calculate the magnitude of this uniformly distributed load? If we know the intensity of omega, intensity of the load as omega, and span of the structure is, span of the beam is L, then the resultant of this uniformly distributed load will be omega L. This is resultant. So the resultant of this uniformly distributed load is omega into L. It is basically equal to area of this rectangle. Omega is the vertical dimension of the rectangle and L is the horizontal dimension. So omega into L is the area of this rectangle, and that is the resultant of the of this UDL. And what about the location? The location of this of the resultant will be through the centroid of this rectangle, which is obviously at L by 2. So when we are dealing with UDL, there are two important things: the magnitude of UDL or the resultant and the location of that resultant. Magnitude of the resultant is omega L, that's area of this rectangle, and location of the resultant will be centroid of the rectangle, which will be L by 2 from either of the ends. Okay. Then there is third type of load that is termed as VDL or varyingly distributed load. So third type of load is VDL or varyingly distributed load. So it is abbreviated as VDL, varyingly distributed load. And if this is the span L, now what, yes, before going to the calculation, what will be the physical example? Let's say we have a beam we provide supports at both the ends. And supposedly we have a heap of sand. Let's say there is some support available, if there is a wall or some wooden partition or whatever, and the sand is heaped over the beam. It may be anything, let's say sand, right? So this sand will apply a triangular load on the beam. And what will be the magnitude and location of the resultant? Magnitude of the resultant, this dimension is omega and span is L. The magnitude of this load will again be equal to the area of the load, and this time the shape is triangular, so the area will be omega into L by 2. So the resultant will be equal to omega into L divided by 2. And what will be the location of the resultant? The location of the resultant will again be through the centroid of this area, which will be, if this dimension, the base of the triangle is L, so the location of the resultant will be 2L by 3 from this side and L by 3 from this side. That's something you already know from your basic mechanics knowledge. In your basic mechanics, you would have studied the geometrical properties of areas, and you would have seen that what is the location of centroid for a triangle. So from this edge, it is 2L by 3, and from this side, it is L by 3. Area of the rectangle is omega L by 2, and that is the magnitude of the resultant of this triangular load. So these are three types of loads that we will be frequently dealing with. And one more thing is that when I say loads, I include forces as well as moments. Sometimes we will also be dealing with point moments, like if I have a simply supported structure, let's say, there might be movement acting on the point, on some point, and this is called point moment. When we will be analyzing the structure, we will see how to deal with the point movement. Right now, what I want to communicate is that in some of the cases, other than these forces, we have some movements as well. How to deal with them, we'll see that later on. Okay. Is everybody clear about these different types of loads? Anybody having any question?
Yes, sir.
All right, that is great. So if we do not have any question now, let's move to the next basic thing. One basic definition is about longitudinal axis, but I think I have already discussed that. Longitudinal axis runs along the longitudinal axis of the, along the length of the member, and it passes in the cross section, it passes through the centroid. And when we draw a free body diagram of any member, we draw basically longitudinal axis. For example, I have shown the beam with like this beam with this line here. So this line is basically longitudinal axis of this beam. Okay. Now next we have a couple of definitions which are very important, and we will be dealing with these quantities throughout the semester. That's shear force and bending moment. Shear force. So what is shear force? So let's see, this is a beam, and if I apply transverse load on that beam, this load will have two tendencies. One tendency is to bend this beam, that generates bending moment. Other tendency is to slide the beam sections against each other. For example, load is acting here, it will have the, and I consider, let's say, a cross section at this location. So at this location, if these are the two faces of a cross section, these two faces will have tendency to slide against each other. And if that tendency is present, that tendency is because of shear force. So if we have a beam, and in that beam, two sections or two parts of a section have tendency of sliding against each other, that tendency is caused by shear force. And there are two types of shear forces that we will be dealing with. positive shear force and negative shear force. What is positive shear force? As I said that shear force is a force which tends to slide one section relative to the other. If this sliding is this way, that left part has a tendency to move in the upward direction and right part has a tendency to move in the downward direction. This is termed as positive shear. So this will be our sign convention. If we have left part of the section moving in the upward direction and right part of the section moving in the downward direction, this is termed as positive shear. And if it's the other way around, if the left part has the tendency to move in the downward direction and the right part has the tendency to move in the upward direction, this is termed as negative shear. So this will be our sign convention when we will be dealing with shear forces. How to calculate these shear forces and how to represent them in a diagram, we will make all this discussion in detail later on. At this point, our objective is just to understand that what do we mean by a shear force. So shear force is a force that tends to slide one section relative to the other. So this is one section and the shear force is trying to slide one section relative to the other. Okay, and similar sliding is present in both the figures. Okay, keep your mics mute, everyone. Keep your mics mute. All right, this is shear force. And make sure that your mic is mute, otherwise it causes distortion. All right, so this is shear force. Next is bending moment. Next, basic and important definition is of bending moment. Now, what is bending moment? Bending moment is definitely a type of movement. In your basic mechanics, you would have studied movement. Now, what is movement? Movement is the rotational effect of force. Movement is a rotational effect of force. Now, if I have a member like this, if I have a member and I apply force in the downward direction here, that force will tend to move the member like this. This movement is termed as bending, and the movement that generates this bending is termed as bending moment. So the movement that causes the beam to bend is termed as bending moment. Now the question that might arise in your mind is that, is there any other type of movement? So the answer is yes, there is other type of movement as well. For example, if I have a member like this, so there may be a movement present in this, with this orientation, that tends to twist the member. This movement, this is again rotational effect of force, and this movement is not bending movement. This movement is twisting movement, or it is also called torque. So we have two types of movements. This one is twisting movement or torque, and the other one, this one that tends to bend the member, that is bending movement. Right now we are talking about bending movement. My entire discussion with you guys will be about bending movement. We will cover twisting movement in this semester as well, but Dr. Safir Abbas will be discussing that. What do we mean by twisting movement? How we calculate torsion corresponding to twisting movement, etc. Okay, so this is bending movement, and we will see how to calculate it and how to present the variation of bending moment along the length of the beam using a diagram. Now, there are, just like shear forces, there are two types of bending moments. if I have a beam, okay, and load X in the downward direction, that load will cause the beam to bend like this. This type of bending is termed as sagging. And our sign convention will be that we will take sagging as positive. The other possibility is that the load might be acting in the upward direction and it will cause the beam to bend like this. This type of bending is termed as hogging. Our sign convention will be, we will take hogging as negative. Sagging positive, hogging negative. And one clarification is that here I have shown sagging under the application of downward load and hogging in the application under the application of vertical load. But depending upon the combination of loading acting and the supporting system, the beam may also hog even under the application of downward acting force. When we will solve problems, we will see that case. But at this point, we need to know that whenever beam bends like this is termed as sagging, and according to our convention, sagging will be treated as positive. If beam bends like this, you may say in the upward direction, we call that hogging, and according to our convention, hogging will be treated as negative. Okay. Is there any question about shear force, bending moment, and our sign conventions? Are these things clear? Or do you have any question about anything that we discussed today? Okay. One more thing about these shear forces and bending moments. We cannot physically see shear force and bending moment. Shear force and bending moments are internal forces, and just through our eyes we cannot see that. You can just think them to be as headache. Headache is there, but you cannot see that, right? Or any form of pain which is present internally, but we cannot see that through our naked eyes. So anybody having any question about today's discussion, because we will be concluding our today's discussion here. Okay, Akmal, please go ahead.
Sir, my question is related to the type of loads.
Okay.
Sir, as you said that UDL and UVL can also be converted into single point load, but then why we have different shear force diagrams and bending moment diagrams for UDL, UVL and single point load?
We will not be treating UDL and VDL as a point load. But I was saying that we sometimes have to calculate the resultant magnitude of the load, and using the idea of or the concept of area of that load diagram, we can calculate the resultant magnitude. Otherwise, we will treat UDL and VDL like UDL will be treated as UDL while drawing shear force diagram. VDL will be treated as VDL as while drawing shear force diagram and bending moment diagram. I'm not saying that we will convert these UDLs and VDLs into point loads. I was just talking about their resultant magnitude. Okay.
Okay, sir. Thanks.
Okay. Any other question? Let me take your attendance one more time for today's session, just to keep track. Okay, so if we do not have any question at this point, then we can stop here and we will continue our discussion next time, inshallah. Okay, so I'll be leaving the meeting now. Allah Hafiz.
Allah Hafiz.
Allah Hafiz, sir. Allah Hafiz.